Hello, welcome to this week's sprint. This week I tried to learn how to use Rust, and I implemented a breadth first search to a Wikipedia API, to see how close different topics are in the Wikipedia graph. Um, so to get started, I'd like to talk a little bit about Rust, why I chose Rust, what I learned from Rust, and a little bit about that. So Rust is interesting for memory. Um, as you can see in my examples, there's two main things. When you first declare a variable, as you can see with x here, x cannot be changed because it's immutable. That is the default for any variable defined. And as you can see with this example down here, test error, if I try to change it later, add 5 to it, then the compiler will tell us. And that's something super interesting about the Rust compilers that's very explicit with how it gets things done. And then there's also lifespan. So let z gets deleted at the end of its block. You can't access it outside, which is pretty basic, but it will get freed up, that memory, which is pretty interesting. Next, compiling. Rust compiles to highly optimized machine code. It is a good reason to use Rust. They can abstract things without taking too much away from it, which is interesting, unlike other programming languages. However, I have my own caveat here, which is that it's an unpredictable layout, meaning you don't quite know what you're declaring if you're declaring a struct. And then you have to import different things if you want to be explicit about that. So here's an example in C. I know exactly where everything is. I know that character is the first 8 bytes, integers the next 4 bytes, and then characters the next byte. But in Rust, it's not guaranteed. And if I wanted it to be guaranteed, then I'd have to include the represent C module, and it's kind of a hassle. You kind of have to know what you're doing to include that. So as a computer engineer myself, working with embedded systems, it's not super applicable to use Rust. However, there are some good things in Rust. I felt like it was easy after learning the Rust syntax to kind of figure out how to use hash maps, vector dequeue, and hash set, which are pretty critical for graph algorithms, which we'll talk about in a second. Pretty much a hash map, it's just a hash, but it's kind of like a dictionary, so it has a key and then a value. And it hashes them, so it's pretty perfect for O of 1 lookups. And then vector dequeue, it's queue, it's perfect. You have to have a queue for graphs to know what you need to visit, etc. So what is this graph? What is a breadth first search? Why do we use it? So graph traversal, we've mentioned this a little bit so far. Pretty much what graph traversal is you can see on the right, there's this tree, a graph. This is a binary tree, but graph traversal is just a way to iterate through that graph to find what you're looking for. So breadth first search goes by layer, and then a depth first search goes all the way as far as it can go in one path, and then it'll backtrack to its last choice and then go all the way farther in the next path. And the main difference is that breadth first searches are good for unorganized data, especially if there's loops, because then you can just go step by step all the way out. We call it depth. And then depth first search is really good for mazes because it will go all the way out and it will backtrack till its last incorrect choice and then go all the way out. So we'll find the answer a lot faster because we know that there's dead ends. However, if there was a loop in the maze, then it wouldn't work super well. Perfect. Now my implementation in Rust, I developed a node. This one's super easy. All it does is it stores information. It stores the hash of its parent node and its own hash, and then a few other variables. One of the more important ones is its visited, whether or not it's visited, which is a bool, right? So that I can tell if I need to check for all of its neighbors or not. Then the graph is one of the more important ones. I guess they're all important, otherwise this wouldn't work. But it owns all the hash maps, the queues. It keeps track of things. It is the entire graph. Um, Pretty much the main important thing to note is that um, the way that I run the breadth first search is by this step function down here. This step, these two steps, I guess, they are what iterates through one node of the graph. DQs, queues new ones, etc. And then I've got the next page. This is the driver, pretty much. So this is the breadth first search. Pretty much all I do is I make a new graph. I give it its end goal. And then until it finds the node, I keep on calling the step. And here is it in application. So as you can see here, I'm going to navigate from Rust to software in Wikipedia. And then, oh, what the? Let's move back some. So Rust to Wikipedia, and then it initializes. And it increments the search every 100, just because it makes it the program run faster. But that's just to see if it's doing anything, mostly for debugging purposes. And here we are. Come on now. Okay, as you can see, it goes from Rust to table to software in 26.06 seconds, which is pretty fast. I've definitely had a lot slower programs. Perfect. So this next one this is just optimizations that I had to do. So time per step at first was a third of a second, which made for 1,000 checks about 56 minutes. So I had to implement different things, and that was after my first optimization, which was a hash queue. So I used a queue and then a hash queue just to make sure everything was kept track of, and I wasn't re-adding things to the queue, because that would just increase it if there's two of the same node. Cool. And then refactor node and step. I just had to add more things. I made step in the graph function in charge of calling the wiki API and searching for all the related sites. Then bulk hash search, I instead of checking each individual site I got from the wiki API to the to our previous hash, I would add all of the new ones together, and then match the two hashes in their entirety, and then the differences I would add to the graph. Then async conversion, before I was using a more static approach, and it happened that this conversion actually slowed down the program, which I thought was interesting. But the reason I converted was so that I could start doing these more frequent implements. So with async functions, you can do the same function multiple times concurrently, and then combine it later to a future. And I thought that was super interesting and something interesting to learn about. Perfect. Now, to optimize this even more, I did implement bidirectional breadth first search. What this does is starts at two ends, and since we know both ends, this makes finding connections easier in depth graphs. As you can see on the right, it kind of minimizes how big the graph gets if I wanted to go, to a depth of 6. And that's kind of the example down here with this big O notation, is that one directional breadth for search is breadth raised to the depth, whereas bidirectional breadth for search is breadth raised to the depth divided by 2. And just for this example right here, where it's a depth of 6, 1, 2, 3, 4, 5, 6, then it takes O to the 64 to reach the end. Whereas for bidirectional breadth first search, it's O to the 8, right? Perfect. So After that, we implemented more or less something super interesting, which is, well, I had to implement this. Sorry, I wasn't looking at my slide there for a second. So we had to implement this bidirectional breadth first search. And what I did was I made 2 graphs this time, and then I would send in the other graph's hash table. And I check that entire hash to see if there's any connections. And that's kind of how you check the farthest layer out. And then doing that on both of them and alternating each one, it was able to speed up the process a lot more. So here we are, we're going to do the same exact search, which is Wikipedia, to software, and there's going to be a big difference. So yeah, it was less than a second. And then here I go through another one. I believe this one is the Cold War. So the Cold War and Dr. Pepper, which is just an interesting kind of thing. And there is something interesting, is that the Wayback Machine. And I'll talk about this in a minute, just but you can't see that it does do it. But this is a erroneous kind of breadth first search tool. Anyway, for accurate ones, why is Dr. Pepper to the Cold War inaccurate? Because it uses the Wayback Machine. There are certain identifiers in the Wikipedia API that I was trying to get rid of, but I wasn't able to completely. And they're just kind of like teleported from crazy different things to each other, because at some point in the Wikipedia page it links to it, even though I tried to only have the main text links included. But it was just a little bit hard to figure that out. Anyway, for Rust programming language to software, the time was 0.98, which is a total depth of 4 or 3, which is the start, and then 3 more. And then Hot Wheels to Cold Case, it was also 3, but it took a little bit longer. And then Bill Gates Bass Pro Shops Night Race, which is a NASCAR race, it was also 3 iterators, and it took a little bit over 1.5 seconds. So thank you so much for watching. This has been my breadth first search in Rust, minimizing connecting links in Wikipedia. Thank you.